turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
Discoveries,
Advances.
questions,
Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith. Coming up, a particle with a record-breaking energy gets discovered, but where did it come from? Also, damaged hearts healed using stem cell patches of tissue. Human clinical trials are about to kick off. And a bit later on, the project using quantum mechanics to revolutionise the London Underground.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, scientists have announced the detection of a particle zipping through a detector 3 kilometres under the Mediterranean Sea with record-breaking energy. In fact, it was carrying 30 times the power of similar particles detected to date. It was a neutrino. These are tiny particles 1,000,000 times lighter than an electron that emerge from nuclear reactions, including the fusion processes at work inside stars. And these neutrinos from these sources usually have a certain range of energies, but nothing like this new event, which was picked up off Sicily in February 2023 by the KM3net detector. They think it might have come from another galaxy. But what could have made it? It certainly defies explanation based on our present knowledge of physics, which is what makes this so exciting. I asked Ben Alanak, Professor of Theoretical Physics at the University of Cambridge, to take me through the paper, which is out in Nature this week, describing the announcement.
This is a measurement by the KM3net collaboration. They're an experiment in the Mediterranean Sea. They're what's called a neutrino telescope, and they've measured something which they interpret to be the highest energy neutrino ever measured.
You better tell us what a neutrino is.
A neutrino is, as far as we know, a fundamental subatomic particle. It's emitted in nuclear reactors, for example, and also by the sun. So nuclear reactions, it gets emitted, and at places like CERN in particle physics experiments.
And what do we know and what do we not know about it that makes this paper important?
The neutrinos that we see are a new window onto the universe. That's why it's worth doing this kind of experiment. We're used to looking through telescopes with light, but light gets absorbed by matter very readily. But low-energy neutrinos will pass straight through the Earth without noticing it, for example. Okay, they start to interact when they get higher energies and so on. But sometimes you want to see places that you can't see with light. So, for example, if you want to detect what's going on in the middle of the sun, you use neutrinos because they will travel out of the sun and you can detect them.
If they don't interact with anything, how can we detect them then?
Well, that's a bit of an exaggeration I made. They just interact very infrequently. So although 1 in 10 billion will make it through the Earth, the odd one will interact. Those are the ones that you detect. So you tend to have very large detectors. And in this case, it's a cubic kilometre of the Mediterranean that you're using, putting detectors around it to detect light to see a neutrino interacting with the seawater. And then that produces products that you can see the light from.
I see. So the neutrino, 1 chance in a billion or something, hits something, interacts with it, and produces a flash of light. And it's the light that we see, and that tells us that interaction occurred.
Yeah, exactly. And what this experiment has seen is a hell of a lot of light, meaning it was a really energetic neutrino. It's got the energy, they calculate it's got the energy of about 10,000 times the collisions that are happening at the Large Hadron Collider at CERN. So that's huge.
How do they know it's limited just to neutrinos? Could it be some other exotic thing that we've not met yet that's done this, and we think it's a neutrino and it's not?
There are no other exotic things that we know about that this could be. There is another particle that is in cosmic rays that sometimes has quite high energies that we see. And so you have to rule this out by properties of what they measure. These are called muons. And a muon at this energy will go through less than 60 kilometers of seawater And this one came in horizontally through the med, so it went through at least about 300 kilometers. So muons are ruled out. So it's kind of a process of elimination. Everything else that we know about doesn't seem to work, and so but a neutrino would work, and so it's proposed that it's a neutrino. But of course, there is some inference in that, and detective work and so on.
When a nucleus decays radioactively, it can spit these neutrinos out. We know they exist. They fit into our model of the fabric of the universe. So what determines how much energy they have? And why is this one, therefore, a bit special?
The thing that's decaying, that is spitting them out, basically what happens is the mass of that thing gets turned into the energy of the neutrino, or at least some fraction of it. So if the mass is, something... that's present in a nucleus, the energy isn't very much. But if the mass was whackingly large, or the original thing was accelerated by around some star or something, or some black hole very quickly, and then it decayed, then it could give the neutrino a lot of energy.
So we have a sort of theoretical idea as to how much energy a neutrino would normally have based on the physics we understand, but this one's off the scale, and argues that there has to be one of those two scenarios happening to it. Either it's some massive thing that we've not discovered yet that produced it, or something we do know about got accelerated very, very fast in the process, and so it had extra energy for that reason. Are those the two scenarios in summary then?
Yep, absolutely. And the first one is, to a particle physicist, is extremely exciting, because this would be a totally new form of matter. And so that's why why in the particle physics world, there's a lot of excitement about this story. But, astrophysically, how do these things get such huge energies anyway? That's also an interesting question, right? So either way you look at it, we're going to learn something about the universe.
Obviously, with any kind of discovery like this, it's an initial observation, it needs confirmation, and you've got to have a questioning mind whenever you see a paper like this. So when you read this, what went through your mind in terms of the yes, but sorts of questions?
Well, initially, I wondered what IceCube had seen. IceCube is a similar experiment. Instead of using Mediterranean water, they're using Antarctic ice. But it's huge, it's even bigger, and it's been working for much longer. KM3Net only worked for 1 year when this event cropped up. But
they haven't seen it.
They haven't seen anything like this energy. The highest thing they saw in all of that time, in that 15 years, was a 20th of the energy that KM3Net saw. So unless they got incredibly lucky, there's something funny going on. We'd like to understand what's happening. Why did IceCube not see it? Now, they're in a different location. There's some bits of the sky that IceCube can't see, because very high energy neutrinos like this wouldn't go all the way through the Earth. They would be stopped by the Earth. However, because this thing came in horizontally, it looks like IceCube should have been able to see events like this if it was some very heavy particle being, just sort of decaying isotropically. So the next thing you think about is point sources. Could it be some astrophysical point source that produces these things? And they look at there are catalogues of high energy neutrino producers, and this doesn't seem to point back to any of those. So the current most likely possibility that people have thought of, it's some transient source. That means it's an astrophysical source that wasn't switched on until between 2022 and 2023 when KM3Net switched on. IceCube just sort of missed this one. They were very lucky and saw it, but this is a case where we definitely need more investigation.
Ben Alanak at the University of Cambridge on the mega-energetic neutrino from a galaxy far, far away. It goes without saying, we'll be watching this space to see how that story evolves. Now, back here on Earth, scientists in Germany have found that damaged hearts can be repaired using small patches of heart muscle grown from stem cells in the lab. These findings, which have been published in Nature, could give new hope to millions of people with advanced heart failure. Sanjay Sinha, who's Professor of Cardiovascular Regenerative Medicine at the University of Cambridge, also works on this technology, and he's been telling me how this works.
It's trying to tackle the problem of heart failure, and that's when hearts are damaged, often by a heart attack, and we've got about 1 million people in Britain who have heart failure. They can't do the things that you and I would want to do, walking upstairs, whatever. They get very short of breath, and they have a shortened lifespan. we don't have a good treatment for these patients that will bring their hearts back to normal. So the idea here is to use stem cells to try and mend that gap.
And what shape does that mend take? What actually is the application of the stem cells? What do they do?
So stem cells are cells that can turn into any cells in the body. And what this group have done is they've used stem cells to make heart muscle cells, and then they've seeded these heart muscle cells into a patch. They made a cardiac patch, basically. So it looks like a piece of heart muscle that's contracting away. And they've used it to actually stitch onto the hearts of monkeys who have had heart attacks, and then to see whether that improves heart function.
Does it?
Yeah, absolutely. Even 6 months after it's applied, the heart function is improved in these monkeys. The heart cells that they put in are still alive and beating and contributing to heart function. It's absolutely wonderful to see.
Is it a meaningful contribution, though? So if that was a patient, the thing they would say is, I can't get up the stairs, and now I can get up the stairs. Do the monkeys show a significant improvement, or is it just, yeah, it's working, but it's not making much of a difference to their quality of life?
Yeah, that's a great question. It's certainly improving heart function. Quality of life is a bit more difficult to measure, and I think those studies will actually happen once we start to do this work in patients, and that's when we'll really know how well it works.
When you look at the heart that's had this done to it, what does that patch actually do? Does it wire itself in? Because the heart's an electrical organ, isn't it? And there's electrical signals flowing all over it that make all the cells beat in synchrony and so on. So does that work the way we would hope it would when you do this?
What's interesting is that the patch, it doesn't electrically couple to the heart, but it does contract in synchrony to the heart. We don't know exactly how that does it, but it might be mechanical forces. That means that the patch and the heart work together. And we think that that contracting together helps the heart to function better. But there's probably other factors as well. We think the patch probably releases substances that make the rest of the heart, the damaged heart, contract better as well. So there's probably many different things going on here.
When you look at a heart that's been damaged by a heart attack, often the area that was affected, it forms a tough scar, which makes the heart very stiff. So do you have to remove that and then put the patch in, or does the patch slowly get rid of that? I mean, what does it look like when they look down the microscope in the aftermath of doing this?
Yeah, there is a scar there, you're absolutely right. You put the patch actually on the surface of the heart, so on top of the damaged area, so you don't remove the scar. So it doesn't change what's underlying, but it just adds extra muscle on top of the damaged area to try and help the heart to contract.
And how long did they look for with these monkeys?
Oh, for 6 months after they implanted them. And even at 6 months, the heart was showing better function, the transplanted cells were present and working away.
So it looks like it does have the potential to have long-term contribution. It's not one of those things where the cells are going to expire pretty quickly or get removed by the immune system or something.
That's exactly right. This is one of the nice things and very promising things about this is that it suggests there will be long-term benefits.
Where did the stem cells come from? Were they the monkey's own cells that got reprogrammed, or was this sort of an off-the-shelf batch of stem cells that got turned into heart cells?
So they did both. They did some studies where they took skin cells and turned them into stem cells. So the monkey got its own heart cells back, in other words. That monkey didn't need any immunosuppression. But other studies they just used generic stem cells where it was given to different monkeys. And those monkeys had to have their immune response suppressed. But that's the same sort of immunosuppression that a patient who has a cardiac transplant might have. So it's a kind of immunosuppression that we're familiar with and we can use clinically in the future.
What does this add then? Because people have been trying to build these patches for a long time. They've done this sort of thing in small animals like rats. This is the first time they've done it in monkeys, isn't it? I think I'm right in saying that, aren't I? So what does this add then? Does this give us confidence to go into the clinic now?
Yeah, absolutely. It shows that it's safe. It shows that it's effective. It's the springboard for going to clinical studies. And in fact, this group who have done the work in the monkeys, they've used this to get approval for clinical trials. And in fact, the paper shows one patient who's had a patch who then subsequently went on to have a heart transplant. So they were able to look at the heart and they could show that that patch in the patient still had heart cells surviving. So there's a clinical trial now ongoing to see how well these patches work in patients. So that's the impact of this piece of work.
Thanks to Sanjay Sinha from the University of Cambridge there.
The Naked Scientists podcast is produced in association with Spitfire, Cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound. Perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith. Still to come, whether botanic gardens can help to save endangered wild plants and flowers. Before that, though, rumbling beneath the streets of England's capital for over 150 years, the London Underground is the oldest and among the world's largest metro systems. But when you have a system this complex, and it's mostly all underground, knowing where you are is much more of a challenge. At street level, of course, I can whip out my phone and use GPS to determine my location and which way I need to go to get to, for instance, South Kensington Station. I can't do that, though, the minute I go down their escalator and onto the underground. The GPS signals are blocked. So keeping tabs on where all your trains are so you can operate things at peak efficiency, and that includes tracking down what precise bits of the network need maintenance, has been a long-standing problem. And this is why I've come to South Kensington, because there's a project afoot near here to combine cutting-edge quantum mechanics with tube trains. Transport for London engineer Steve Foote.
So the London Underground network's really complicated and extensive. We've got 11 lines, there's 272 stations. We move approximately 1.2 billion people a year. We have 400 kilometres of track, and then we've got 5 different signalling systems. So it's a really complicated system to operate.
I've joked in the past, but it's actually true. You're moving more people under the streets of London every day than the populations of whole countries, like Sweden, for example.
I am still amazed at how complicated the system is and what we achieve each day, yes.
So tell us about the problem that, as you see it, that having better positioning of trains could help to surmount.
In terms of improving the way in which we maintain the asset and become more efficient and effective in the way that we do that, then having data is fundamental. Obviously, modern technology would allow us to use the train as a sensor, and it could run down the tracks, collect data around all those assets. And then if we've got an accurate positioning of where that train has collected that data from, if there's an issue, we know exactly where to go back to collect that data. And if we keep running the trains and keep collecting the data, you can then start trending the changing condition over time. But you can only do that if you know that you're capturing the data in the same place each time.
I was talking to someone the other day who's working with car manufacturers. They're collecting data collected by cars as they drive across the country's roads. They're kind of regarding cars now as a sensor on wheels. They know where the car is because they have GPS. In a tunnel, that presumably does not work.
That's correct. GPS, you can't rely on it in the underground sections of our network, and therefore an alternative form of accurate positioning is needed. The technology that signalling uses identifies the section of railway that the train's operating on, but it doesn't give you the absolute position. So if you want to go and identify where there's a defect on the railway, you need the absolute position to know where to go to.
Got it. So you know a train is on a section of track between 2 signals, but if it has encountered a bump in the road, you don't know where that bump is except it's somewhere between A and B. Whereas if you had a really precise way of keeping tabs on where the train is at any moment in time, you could say, that's where the problem is, that's where we've got to send the repair guys to.
Yes, so the signalling system uses a train being in a geographic section in order to keep the trains safe, keep them separated. We do also have other infrastructure installed on the network, but it doesn't give you that accuracy we desire. So using quantum sensor could give us the level of accuracy such that we could do, similar as you described with the cars, use a train as a sensor to look at lots of different assets.
Steve Foote. And this is where Dr. Joe Cotter, a physicist at Imperial College London, comes in. He's pioneering quantum sensors based on clouds of supercooled atoms, the movements of which he can read with exquisite precision and accuracy using a laser. And by adding up all the movements the atoms make, you can work out how far and how fast the thing holding them must have moved. In this case, that would be a train, but it could equally be a boat, a car, or a plane. In other words, this would give us another way of keeping tabs on position, but without relying solely on mechanisms like GPS, which can sometimes fail or even be misleading.
In my labs, what we're doing is developing a new kind of sensor that harnesses quantum mechanics to make more accurate measurement devices. One of the nice things about this approach, so inertial navigation, is that the ability to position yourself is self-contained in the vehicle that you're travelling in. So you don't rely on anybody outside. It's all on that vehicle.
In basic terms then, what is inertial positioning and how does that actually work? Before we get into the quantum way of doing it, what's the basic principle?
So inertial navigation relies on measuring the motion of the vehicle that you're in. So in particular with the acceleration or the rotation of the platform. And then you have to do some maths to convert those measurements of inertial signals into a change in position in a map frame. So for the London Underground along the track, for example.
So if I reach in my pocket, take out my phone, it knows that it's moved upwards, sideways, along a bit, at what sort of rate, over what sort of time, and it could then work out, working backwards, doing that maths you mentioned, where it must now be relative to where it started. Is that what you mean?
That's exactly right, yeah.
And you're saying you want to do that with atoms, quantum level, tiny particles. Why do we need to go any further and use atoms?
By harnessing quantum mechanics, we think we can make more accurate sensors that could enable you to navigate for longer in the future. So it's about a next generation kind of approach to this inertial navigation.
How does it work?
So for our quantum inertial sensors, we start by laser cooling a cloud of rubidium atoms to a few microkelvin in temperature, about a millionth of a degree above absolute zero.
And why do they have to be that cold?
When they're cold like that, their quantum properties start to come to the forefront. And so to describe their motion, we need to treat them like waves. And it's that wave-like nature that we take advantage of in our sensors.
How does that work then? We've got a sensor, it's got these very cold rubidium atoms. How do they know where they're moving? And how do you log that? How do you extract that information?
We have a laser and we release our atoms and the atoms interact with the laser. The laser is essentially just a wiggling electric field and we use those wiggles like a ruler. And so if it's fixed to the vehicle and our atoms are in free fall, we just measure how many of those wiggles in the laser the atom moves through in a given amount of time.
Put simply then, if the atoms are in one position and the train moves forward, the atoms are left behind a bit, so they're going to move down the ruler a bit, your laser ruler, and you can register that, and that would correspond to an acceleration in a certain direction. Is that how it's working?
That's exactly right, yeah, that's the principle behind it. We've taken demonstrator systems on the tube already and we've had some success.
What you took, basically, I've seen your gear in the lab here, it's a whole room. So how on earth did you get that on the Underground?
So we've packaged up one of our sensors and deployed it on a London Underground train.
Did you get any funny looks? Other passengers look a bit strangely at you.
It was a test train, there were no passengers.
Okay. Can it work in 3 dimensions? You've mentioned a sort of ruler analogy. That's one axis. Can you do this in multiple axes so that you've literally got a tracking in 3-dimensional space system? Because that's going to be needed. If we're going to need to know where an aeroplane is or a boat or something, we're going to need all of the degrees of movement to be tracked.
Yes, absolutely. So in the laboratory, we already do it in 3 dimensions. For the transportable work we're doing with TfL, we're focusing on just one axis for now, just to overcome these engineering challenges and environmental challenges. But no, you're absolutely right. The next step will be to develop a new 6-axis sensor for the railways.
Joe Cotter, another London Underground engineer who was actually instrumental in getting this collaboration off the ground, is TfL's Steve Venables. I asked him if they can get this to work, what sort of a difference it might make.
This has potential to change the landscape of how we operate our railway. If the railway breaks for some reason, we'd be able to fix it quicker, cheaper and more efficiently. And we'd also be able to understand how that asset's performing so we can fix it before it does fail.
I also like the juxtaposition of one of the world's biggest and oldest railway systems lining up with some of the world's newest cutting-edge navigation technology.
Disruptive technology like this has to be looked at. We can't continue doing the same things and expect different results. We need to start challenging how we look at things going forward. And this is just one example of where we're looking to partner with industry, academia, to develop our own internal capabilities.
TfL's Steve Venables there, and before him Joe Cotter and Steve Foote, and that work is being carried out with the support of UK research and innovation. Around 40% of known plant species could die out because of climate change and habitat loss. That is the brutal picture that's being painted by plant and climate scientists. Botanic gardens are one way to conserve and study threatened species, and there have been calls for these institutions around the world to work together to help save wild plants from extinction. But a paper published in Nature Ecology and Evolution claims that botanic gardens are not currently keeping up with the pace of climate change, and that conservation efforts are also being hampered by a lack of international cooperation. Will Tingle went to Cambridge University's Botanic Garden to see for himself.
My name is Angela Cano. I am the Deputy Curator at Cambridge University Botanic Garden, which means that I am in charge of making sure that the collections we have, the living plant collections and other, look good, they are properly identified, and that we bring interesting species to the garden.
With so many species out there in the world, how do you pick which ones you want to be a part of this collection?
One of the things we look for are species that are interesting to research. The other thing that is interesting to us is plants that are rare in cultivation, that are threatened of extinction, and that are interesting in general to the public.
Let's go have a look at some of the particular examples in the study. Why have we decided to start our tour at the wonderful gates here at the Botanic Garden?
Right, so yes, we are here because this is the main walk of the Botanic Garden, and on each side you see a couple of enormous trees. Those are giant redwoods, and next to them is a tiny Wollemi pine. The one I care most about, the Wollemi pine, comes from an important conservation project because at the moment there are only 45 mature specimens in the wild. So these are individuals that came originally from the wild and that carry the genetic imprint of the species.
45 is horrifyingly low. I know we talk a lot about, there's only X thousand number of pandas left in the wild, but perhaps we should pay attention just as much to trees then if this is the case.
Exactly, that's very, very low. But the good story about this is that now you find these trees in all botanic gardens. It's one of the most widespread species in botanic gardens. So yes, it is critically endangered in the wild, but there are enormous conservation efforts around it. And what we call the meta collection of botanic gardens are safeguarding these species.
So we're here at, I feel like this is quite a reductive statement, but something of a rocky outcrop. It's giving me alpine vibes. Is this fair to say? What are we looking at here?
Yes, we are at the rock garden, and what we're looking at is a display of rocks showing plants that are adapted to mountain environments throughout the world. The reason why we are here is because climate change is going to affect plants across the globe, and in particular plants that are adapted to mountain environments. These are plants that usually grow in cold conditions, and if the temperatures rise, then they can climb up the mountains and find a new spot where they feel comfortable. But mountains are not infinitely high, so at some point they will completely lose what we call their niche. And so at Botanic Gardens we need to make sure we collect plants from these regions and try to do proper conservation of these species.
Okay, so we've gone from the Canadian redwoods up to the alpine altitudes, and now we're back into the glass houses and the hot houses. We've got a very spiky looking tree here in front of us. What am I looking at?
You're looking at a Pachypodium, so this is one from Madagascar. And this is actually very, very hard now to collect them in the wild because they are highly threatened and they are part of a special list called the CITES. And plants in this genus, Pachypodium, cannot be commercialized. And so that means that, yes, they are being protected from trade, but at the same time, the legislation doesn't make a difference about that with botanic gardens. So we can't do much to promote their international conservation.
Given the length and breadth of the species that you've shown me, the ones that are being conserved here at the Botanic Garden, climate change is coming for all manner of plants in all manner of ways. Are botanic gardens and other means of conservation keeping up with the pace, you think, of this change?
Definitely not, and that's what we show in this study, unfortunately. In general, botanic gardens are not being able to keep the pace of the different conservation threats, and that's because it is really hard to collect these species and safeguard them in ex situ collections. And it's also because the extinction rates are becoming higher and higher, so we have so many limitations.
Starting with that first point then, what is stopping you from being able to go and collect and trade within other botanic gardens to get a good amount of samples and species?
Since 1992, when the Convention of Biological Diversity was signed, that gave countries their ownership on their biodiversity, which is a good thing. But then it meant that it is very hard to do international ex situ conservation, because now we need to go through a lot of different steps, bureaucratical steps, to actually be able to go to a country and collect the plants.
Is there a way around it? Is there a way of renegotiating legislation to say, we are a botanic garden, I appreciate we're not from around here, but we do have the plant that you enjoy, your endemic plant's best interests at hand?
Yes, I think a new conversation should be started about that. But also, I think one of the key messages of this paper is that we need to relocate resources, because what we've seen is that most botanic gardens are in the global north, and those have reached peak capacity and peak diversity. But there are younger botanic gardens in the global south, and that's where actually most of the species occur. So if we relocate some of the resources we have in the global north to the global south, that would potentially promote better ex situ conservation.
Anna Locarno in conversation with Will Tingle at Cambridge University's Botanic Garden. Well, now it's time for another great listener question. Will's ears have been burning with this query sent in by Wayne.
If fire needs oxygen to burn and there's no oxygen in space, how does the sun stay burning? Thanks.
Thank you, Wayne. Fire is the result of the process of combustion. As you rightly pointed out, in a combustion reaction, a fuel is heated and it reacts with oxygen to produce oxides, compounds that contain at least one oxygen atom and one other element in their chemical formula. But the sun's energy comes from a completely different process, nuclear fusion. The difference between fusion and combustion is explained by zooming into what's going on inside the nuclei of the atoms of chemicals we're talking about. Here to help me explain is Professor of Astrophysics at the University of Manchester, Philippa Browning.
The sun creates energy in its hot, dense core using hydrogen as fuel, which is available in very large quantities. The nucleus of a hydrogen atom is a single positively charged proton. Through a series of nuclear reactions, 4 protons are forced to combine into a helium nucleus, which is made up of 2 protons and 2 neutrons. These resulting helium nuclei have less mass than the reacting protons, so this produces a very large amount of energy, as mass is being converted into energy. We can see this through Einstein's famous E=mc² equation. Fusion reactions can only happen at extremely high temperatures, but the core of the sun is at 15 million degrees Kelvin, which is high enough.
So that's how nuclear fusion works. But what's going on with the chemistry in combustion, and how does it differ?
Atoms consist of positively charged nuclei containing heavy protons having positive charge and neutrons with a similar mass but no electrical charge, as well as light negatively charged electrons. In chemical reactions such as combustion, electrons are shared or swapped between elements, but the nuclei remain unchanged. For example, when coal is burnt, carbon and oxygen combine into carbon dioxide. This releases some heat due to the electron configuration moving to a lower energy state. Nuclear reactions, in contrast, involve changes to the nuclei. These may either be fission reactions, splitting heavy nuclei into smaller ones, which is what we use for terrestrial nuclear power, or fusion, as we've just mentioned, in which small nuclei combine into larger ones. Because nuclear reactions involve the conversion of mass into energy, they release far more energy than chemical reactions. The fusion of hydrogen into helium, as we have in the sun, produces about 1 million times the energy per reaction than a typical chemical reaction like the combustion of coal.
So, the sun isn't burning like a fire, it's more like a giant nuclear reactor. Fusion doesn't require oxygen because it's not a chemical reaction, and so the sun will keep emitting heat without the presence of oxygen, as it has been doing for the past 4.6 billion years, and will continue for billions more, until eventually it runs out of fuel. But we've got a little while to go until then. Thank you very much to Wayne for the question, and thanks to Philippa Browning, Professor of Astrophysics at the University of Manchester, for the answer. Next time, we'll be answering this question from listener Dan.
Hello, so I've posed myself a question. Had my parents, my grandparents or myself never received any vaccinations, what are the chances that I'd be here to pose this question? Thank you.
And if you think you know the answer, remember you can have your say on this and all of the other questions on our forum. That's at nakedscientist.com/forum. And if you have a question of your own or an answer to supply for us to help us solve this one, why not write to me? It's chris@thenakedscientist.com. Just before we head off, please do, if you can, give us a donation to support the programme. They are very gratefully received and make a massive difference. You can do that at nakedscientist.com/donate. And thank you very much indeed to everyone who does help us out, both in a one-off capacity but also regularly. Details of how you can do both of those things are at, as I say, nakedscientist.com/donate. That's all we have time for this episode. Join us on Tuesday, though, when we'll be dipping into multiple sclerosis, including why this happens to some people and what we can do about it to make life more comfortable. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. We're supported by Rolls-Royce. I'm Chris Smith. Thanks for listening. And from all of us here at the team, until next time, goodbye.